So, Assalamu alaikum. Today we are going to move to second part of this course. So we give kind of a slate cut through introduction through the different topics that we will go through. One of the important topics in networks is how to deal with connectivity. So if you have a network which is simply a set of nodes and some links between those nodes, how can you figure out what's the best way to reach from one point to the other, as we mentioned, for example, in the functionality of routing, or how you can figure out that there is something wrong with the configuration of the connectivity in this network, such that, for example, there are some nodes that are unreachable. So you have nodes there, you see lots of connections, but reality is one of the nodes is not reachable from many other nodes, right? So how can you ensure connectivity? How can you measure the connectivity? How can you figure out best routes and so on? All this kind of networking or connectivity has a modeling method that comes from, to some extent, mathematics. It's under the topic of discrete mathematics, and it's something called graphs. So graphs are ways to represent different nodes, connections between them, and then being able to analyze or design these connections to establish certain properties, okay? So we'll go through elementary stuff in graph theory. We are not gonna go in depth into the theory itself, but we'll just have a touch on the major theorems and major definitions of graph theory. Now, just the first slide here, before we go to the contents of today, gives you a glimpse of what are the different applications of graph theory. So graph theory doesn't only deal with networks. Again, you can think of, I have nodes and lines connecting them. This can apply to something like networks in general or computer networks in particular, which is what we are looking for here. But also, there are things like chemical compounds. So if you think how chemical compounds are generally represented, you have those elements, right? For example, if you look at the alcohol, for example, okay, in organic chemistry. So you have the C, the carbon, and then you have H's connected to it through certain number of bonds, right? And then O's, different oxygen, and a mix of those connectivities creates different compounds. Each one of them is different from the other, depending on the elements and the connections between them, right? So graph theory can be used actually to look at chemical representation of different compounds. It can also, the same thing that we do in networks can be done actually on traffic and roads, because roads are simply connections between different points. You can think of those points as intersections. You can think of those points as district. You can even think at a bigger scope between different cities, right? So you have nodes, which are the cities or the intersections or the districts of a particular city, and you have links, which are the roads that connects one to the other, one point to the other, right? So the same thing that we can do in computer networks can be done actually in traffic road networks, okay? Similarly, which is very interesting, if you have any two parties connected together by some link, for example, you have time slots and rooms in the university, right? And you have courses that you want to schedule exams for them. And whenever you say a particular course is gonna be, the exam for that is gonna be held at that particular time in that particular room, there is a connection between the course and the room and the time, right? So that connection is a connectivity, and the class room and the time is one node, and the other node is the course name. So you can represent that relation as a graph, which will allow you to analyze it in a systematic way, right? So it's not just when you have to use actual networks, but graphs actually can represent many things. One example, which is not mentioned here, is something like when you have maps and then you have countries that have borders with each other. So those countries are connected. And then you have other countries that don't have a border with that one, they are disconnected. And based on that, you can use that connectivity to analyze things like something that they call graph coloring. So you want to color different countries with different colors as long as they have borders with each other. But if they don't, you can repeat usage of the color, right? So that's again something that can be handled systematically using graph theory. And the applications are endless, okay? So this just to give you an idea that whatever you learn here about graph theory, yes, we will apply it to networks, to connectivity of networks, but it can be applied to many other domains that uses the same representation concept. Today, we are gonna only handle the first 3 parts of this, and then the rest are gonna be handled in the coming lectures, inshallah. So we are gonna talk about, so we are starting to get introduced to this theory. We're gonna talk about some definitions, some types of graphs, and some terminology being used in graph theory, like this is called this is called that, and so on. And we will touch only on 3 very elementary theorems within the graph theory itself towards the end of the lecture today, okay? Okay, buckle up. So let's go on. What's a graph in general? A graph is a collection of 2 sets, okay? One set is called the set of vertices. The singular of that is vertex, right? So a graph is composed from, you can think of these as points, right? We call each one of those a vertex, okay? And links between those points. So maybe this line and this line. So we call this link the edge, okay? So we have a vertex and we have an edge. Sometimes the vertex, rather than being represented by a dot, it's sometimes represented by a circle. The notation in these slides uses a circle to represent a vertex, okay? So either this or that, that's just a node or a point, okay? So you have dots or you have points, and you connect them with links called systematically or formally called edges, right? But they are links or arcs or lines or whatever you like to call it, just to understand the meaning. But formally it's called an edge, okay? And the graph, as I said, is just the combination of those 2 sets, okay? So for the vertices, V, if I have, for example, like 4 nodes, let me call them U, V, W, Z, for example, then the set of vertices in this graph, V, is gonna be the unordered set, so there is no meaning for ordering, it's just the set of those elements. It doesn't matter which one you put the first and which one you put the second, it's unordered, right? U, V, W, Z, right? And if, for example, I have 2 edges connecting them, for example, okay? So 2 edges, one connecting between Z and W, the other is connecting V and W, then the set of edges in this graph is only 2. There are only 2 edges, and each one of these edges is represented by an unordered set of the 2 connected vertices. So the first edge, let's call this E1, and let's call this edge 2. The first edge E1 is simply V connected with W. And the second edge that I have in this graph is Z connected with W. Don't forget, this is unordered, this is unordered. So it doesn't matter. You write it as WV, you write it as VW, it's the same thing, and it's one representation, okay? Now, having that said, we will learn in the next slide that there are cases where you have directed edges. So it really matters whether the edge is coming from one and going to the other or the other way around. Those ones that we have here are called undirected. So these are undirected edges, okay? But we might have a case where this is U, this is V, and the connectivity is with an arrow. So it's only one way. You cannot go back. It only allows you, for example, to move from U to V. Or it means that U is linked to V, but there is no reverse link between V and U. This directed situation is represented by an ordered set, and instead of using the braces, we use the parentheses in this case, and the start is the start point, the end is the end point. And there is a difference. This is not equal to V comma U, right? These are 2 different things. They are not equal to each other, right? While for the unordered, it doesn't matter. V W is the same as saying W V. It doesn't matter. It's the same thing. No ordering. Okay? Okay. Any questions so far? Just definitions. We didn't do anything yet. But still, if you have a question, you can ask. Yes?
Sorry, but those are nodes of communication between.
We are not talking about communication. Forget about communication now. We're just talking about points and connections, relation between those points. Whether there is a relation, then we have an edge, or there is no relation, so there is no edge, no connectivity. That's the abstract. How we will put this into communication networks, those nodes are going to be, those vertices are going to be the communicating nodes, whether they are intermediate or peripheral, and the edges are going to be the existence of some link with certain capacity and certain properties, right? Whether they are connected or not, okay? Any other questions? You can represent the tabadil al-tawfiq by some graph, but it's not that the graph directly means permutations or combinations. It doesn't mean so. Okay? You can represent some actions like doing permutations or combinations using a graph. You can. But graph theory is not directly related to permutations. Graph theory represents nodes and connectivities. Nodes and relations between them. There is a relation or there is no relation. Okay? Yes?
If it was two, if it has two vertices and start from the same point and ends at the same point itself.
Yeah.
It goes different nodes. So it's gonna be
لا مش فاهم start from the same point and end the same point between two nodes ازاي؟
U goes V, then goes to U. Yeah.
ماشي. دول two links. One going from U to V, one going from V to U.
And if it's one 3 point itself, it's gonna be actually one node.
I'm not getting the question. So let's say I have 3 points, and then what will happen? Huh? What do you want to do with 3 points? Huh?
Like it's connection between each other. 3 of them.
Directed or not directed? Which one?
I mean, like first point goes to the second goes there, and third goes to the
Yeah, so-
the actual full loop.
So what's the problem? What's the question?
And I mean, how to represent it?
Again, 3 edges, 3 points. So if this is U, V, W, and you are saying I have a connection here, I have a connection here, I have a connection here, right? Okay, so 3 connections. What are the connections? U, V. What's the second connection? V, W. What's the third connection? W, U. Where is the problem? Yeah, so you can do it. I mean, there is nothing preventing this from happening. Okay? Any other questions? Okay. This is the part that I already described earlier, but it's formally represented here. So you can have in the edges, there are 2 types. Either the directed one, and we said that this is represented by an ordered set, right? That you see here, and ordering does matter, and it will always have some arrow to show you where it starts, where it finishes. Or you can have an undirected, so there is a link between U and V, and by default this means it goes both ways. It doesn't matter. Whether you start from U, you can end up in V, or if you start from V, you can end up in U. There is nothing preventing this from happening. We call that the undirected, and in that case it's represented by the unordered set, which is put into braces instead of parentheses that we see up there, okay? There is one more type of connectivity that we have to keep in mind, which is called the loop. So a vertex is connected to itself, right? So the loop connectivity, right? And that one, if you want to represent it the way we agreed on, it's gonna be from U to U. It starts at U, it finishes at U, right? So to cut it short, we just represent it this way. So if you have a connectivity in the set of edges that says something like this, this means immediately that you have a loop on U. There is some edge that starts on U but goes back to U without passing any other edge, any other vertex, okay? Now, a question for you. Is this a directed or an undirected edge? What's the other direction?
Doesn't matter.
So it's undirected. It starts on U, it finishes on U. You do the arrow this way, you do the arrow that way, you do the arrow that way. It doesn't matter, right? So even though the graph here shows this with an arrow, but this representation is not wrong, but it can mislead you, right? It says that it is directed. Yeah, okay, but it's actually, it doesn't matter, because no matter how you do it, it's the same. It starts at you, finishes at you. Do you have any other option? Right? So the direction here does not have a meaning. That's why we represent it this way. It's unordered, because ordering would not matter. You put you first or you first. What does this mean, right? So there is no ordering here, and then even though it shows on the graph, the loop shows with an arrow just to represent the loop, just to tell you that this is connectivity, because if you do it without an arrow, it will look weird, right? But this is just, but it is actually an unordered link. The loop is by default unordered. What's your question?
Doctor, I think this doesn't have any meaning.
No, it has a meaning. When you represent things, it has a meaning. Sometimes, for example, when you connect to your computer, you say 127.0.0.1. This is looping to yourself. So your client and server are at the same node. So you are creating a connection with yourself. So it has a meaning, it has applications. Okay?
Doctor, what if we have U and V directed, and then the V goes back to the U?
No problem. Yeah.
UV is equals to V.
No. This means we have two directed links between U and V. This is different from having an undirected link. So if you want to represent what you said, so I have U, V, right? And I have this, and I have this, right? A representation of this would be U, comma, V, and then V, comma, U, which is not the same as saying I have those two, U, V, and I have a link between them, which is represented as just U, comma, V, right? And that's it. Okay? These are two different graphs. They are not the same graph. Later on, we will see that they will have different properties, but later on, okay? Any other questions? Yes?
Can I have two different undirected links between U and V?
Yes, that's what's coming here. Multiple edges. So it might happen that you have, this is the next one here. So you might have this, and you have this, and again, another undirected one between U and V. The way this is going to be represented is U, comma, V, comma, U, comma, V. I have two. It's not one. It's not the same as having just one link. For example, later on, this might count as extra capacity, a reliability link that allows you to fall back. If one breaks, the other works, and so on. So you want to show that your graph is actually connected by two undirected links, not just one. Okay? خلاص يا شباب. Any other questions? زي الفل. Next. Simple graph is a graph which includes only undirected links. So there are no directed links at all. Sometimes they call it undirected graph. Sometimes they call it, or most of the time, they say a simple graph G has this set of vertices and this set of edges. Okay? So whenever you hear the word simple graph, it means that all the edges in that graph are undirected. There is no directed link in the graph at all. خلاص? We need to get practice to the word edge instead of saying link. Okay? I keep using them interchangeably just to get your attention, but later on, everything formally will be represented as vertex, edge. An edge is a link, a vertex is a node or a point. Okay? So if we say a simple graph, it means all the edges in the graph are undirected. Okay? And the example that you see here, the graph G, which is composed of the set of vertices V and the set of edges E, is defined as, here is the set of vertices. So you have 1, 2, 3, they are listed here. And then you have the set of edges. You have one from U to V, this one, right? You have another one from V to W, again, undirected. And you have the last edge is connectivity between U and W. That's the last one, okay? So this is how you fully define this graph. And since all the edges here are undirected, we call this a simple graph. Yes?
Is U to V and V to U the same thing?
For undirected graph, yes, it doesn't matter. That's why you did not attend the start of the lecture, right? Yeah. So when we say an undirected edge, it means that this edge, it doesn't matter. You list it with between braces like this. It doesn't matter whether you say UW or WU, it's the same thing. Okay. If it's directed, we use parentheses and then it matters. UV is different from VU. Okay? Any other questions? Okay, some terminology related to undirected graph. If U and V are adjacent, okay, then this means if we say that U and V are adjacent, this means that there is an edge UV. This is for undirected graph, okay? So we say U and V, the two vertices U and V are adjacent. This immediately means that there is an edge between them. Okay, so this immediately means that I have an edge which is UV. Okay? And also, if we want to relate the edge to the vertices, we say that the edge E, okay, is incident on the two vertices U and V. This immediately means that this edge is actually connecting U and V. Right? Okay? So that's another terminology. The incidence of an edge on vertices. I will give like a small write-up here that probably will clarify the confusion if you have any. And then also we can say that the edge E has two endpoints, U and V. This means that this edge is connecting U to V. So we have an edge between U to V. So simply put, okay, if I tell you that you have an edge and let's call that edge E, okay, which is incident on U and V, then this means that the edge E is actually U, V. Okay, so that's an edge in your graph. Similarly, if I tell you that U is adjacent to V, this simply means that you have some edge, let's call it E again, okay, which is connecting U to V, because they are two adjacent vertices. Okay? Similarly, if you say that I have an edge E which has the endpoints U and V, then this means that E is U, V. So all these statements are telling the same thing. I have some edge E, which is incident on the two vertices U and V. This means that the edge that you have is UV edge, right? Connecting U to V. Or someone tells you that U as a vertex is adjacent to V as a vertex. This immediately means that your graph has an edge between U and V. So here it is, okay? Similarly, someone might tell you that I have some edge in this graph, and that edge has two endpoints, which are U and V, right? Then again, it's the same meaning. Those three things means the same thing, that there is an edge which is connecting U to V, and it's an undirected edge, okay? Now,
What's the meaning of adjacent?
two things are adjacent and they are next to each other. That's the translation, يعني. جنب بعض يعني. Okay? Any other questions? This is clear. So all these terminologies, they exactly mean the same thing. And you have an undirected edge between U and V. تمام?
So edge you mean the line, right?
Yeah, we said that at the start of the lecture. Okay, now comes another important definition. Okay, degree of a vertex. So a degree of a particular vertex يعني node, تمام? a degree of a particular vertex. So if I have a vertex here, and I have, let's say I have this graph, and I have these connectivities, for example, okay? Sorry. Just like this, okay? And then if I ask you, what's the degree of vertex U? Yeah, so the degree of a particular vertex is the number of edges that connect to that vertex, right? So the degree of U is gonna be equal to 2. Degree of U is equal to 2. What about the degree of V? How many edges are connected to V? Only 1. So the degree of V is equal to 1. What about W? There is only 1 edge connected to W, so the degree of W is equal to 1. Okay? So that's the definition of degree. Now, under that definition, there are 2 important cases. One of them, the name is not that much used. Okay? So saying a particular vertex is a pendant vertex, which means that it has degree 1. So that, for example, covers W and V here. Each one of them has degree equal to 1, and we call that a pendant vertex. But that naming is not that much used. The more important and very critical one is when you have a vertex that has a degree equal to 0. It means what? There are no edges connected to it at all, right? That is isolated because it doesn't have any connection with anything, so that naming is important. A vertex is called isolated if its degree is equal to 0, which means that it doesn't have any edge connected to it. It doesn't have any line connected to it, okay?
Even it was loop?
Even no loop.
No loop.
No loop. A loop counts as a connectivity, okay?
Counts twice, doctor? Loop counts twice?
We'll come to that. Good question, but we'll come to that. Okay. طيب, taking this information, let's try to solve this like very quick example, just to get you used to the graph stuff. Okay, so we have a graph G, which is represented by vertices U, V, W, K. And for convenience and standardization of answer, I just placed the vertices in space, okay? And the question now says, also in that graph, the edges that I have are 2 edges, an undirected edge between U and W, and another edge between U and V. Both of them are undirected, okay? First part is draw this graph. So you have the edges now, link them, tell me how they will link, and then find the degree of all the different vertices. Tell me what's the degree of U, what's the degree of V, what's the degree of W, what's the degree of K. Answer it, and I will come and just have a look at what you did. It's very trivial, but should be taken like 1 minute to finish, or maybe less. Finish? Come into you. Okay, وانت قافل الديجريز جنبه. تمام. Great. صح.
هو نفس اللي رسمته انت.
لا مش قوي يعني. في حاجة زيادة. مظبوط كده. كده دكتور بس مسكين. بص الفكرة عندك just a line. Directed is your heart. And we put it, we use parentheses, right? Not braces. If this was written as U, W, then that's directed, right? صح.
لا هيتبدل.
لا نهار ابيض صح. بس هتكسر خلاص صحيح تاني. خلاص صحيح شوية. دي أكون صبح Even why do we? Where are the agents? These are just the disease, right? Use V, W, use V, W. We have them. Now the edges. What do we have? U, W. That's one edge. That's it.
انا مش تبع الامتحان بس انا عندي قلم بس نعرف على زمان هو سنتين هو ده مكتوب
يقول لك ايه لازم تحط لها حاجه ما ينفعش تسيبها لوحدها. جدعانه هي العمليه ماشيه بالجدعانه. ماشي. اوكي شباب خلاص it's a simple example. I saw all of you almost have been able to solve it. So we have only two connectivities, the UV and the UW, right? UW and UV. These are the two connectivities that we have. If you count the degrees of this, around this there are only two links, so that's degree 2. If you count the degrees of this, you have only one coming to it or going out of it. It doesn't matter because it's undirected. So that's degree 1. This one also has degree 1. This is not connected to anything. There is no links to it. So it's isolated and it has degree 0. Any questions?
Can we build the network knowing only the degrees?
No, because you might have multiple solutions. I mean, you can, but you might have multiple solutions. Yeah, it's not necessary that it will be a unique solution.
You could go with, you can go to K.
Hmm?
You can go to K, and the degree will stay be the same.
You,
For example, U to K.
but again, no, but it will not be the same because in that case, well, actually it might be. So if you have U going to K, it's going to be the degree of V is equal to 0, but it's not the same. Degree of V is equal to 0, degree of K is equal to 1, degree of V, if U is the same, degree of W is the same, but the whole set of degrees is not the same.
Yeah, that's
So it might be, I don't know. It might be that there is a unique solution. I don't know. I don't have an answer to this immediately. And I'm trying to think of it. Any link that you will change will play with the degrees of one of the vertices. So yes, we can. Now, if you define the degrees of every single, and it's undirected graph, and you define the degrees of every single vertex there, you don't leave anyone out, you don't leave anyone not described, then definitely you can, there's a unique solution for that graph. Yeah, that's a good question, very good question.
U has two edges, but one of them is direct. Is also counted?
Yeah. Directed is counted in a different way. Because directed is counted as in or out. It doesn't just count as one connectivity. It counts as a degree in or degree out. We will come to directed in a slide, in the next slide, okay? Any questions related to this, ya shabab? Okay, your question is coming here. So for a directed graph, ya shabab, for a directed graph, right? The edge, the directed edge in this case, UV, so this is coming from U going to V, okay? Is, you can say it is adjacent to U, okay? Sorry, based on this, you can say U is adjacent to V, okay? Or you can say V is adjacent from U, because this is directed, right? Remember in the undirected, we just said that U and V are adjacent. That's it. We didn't say adjacent to or adjacent from. Here, you have to specify. So for U going to V, the directed edge from U to V, you can say U is adjacent to V. So you start from U, you go to V. Or V is adjacent from U. So again, you start from U, you go to V. Okay? If it was the other way, then you flip this. So you say V is adjacent to U, or U is adjacent from V. Okay? That's one thing. And the two vertices, U and V, are called the initial vertex, the one that the edge starts from, and the other one is called the terminal vertex, the one that the edge terminates at. Okay? Okay. Then based on that, when we are counting the degrees of different vertices, we need to be careful to count two different counts. One for the n degree, and that's represented by the word big, and then we put a minus, a small minus up there, okay? This is the number of edges which finishes at U, n, coming to U, terminate at U, okay? This is called the n degree, and it's represented by degree minus, coming in, okay? The other one is the out degree. This is the number of directed edges that are leaving, initiating from U. Okay? So for example, actually we have the example down there, so we'll try to solve it together. Or you will try to solve it and I will correct it, okay? But just quickly, for example, if I have this, U, V, okay? Then, why? I don't want to edit. Okay. So if I have this directed from U to V, and I ask you, what is the degree minus of U? This means what? What's the meaning of that? First, before saying zero. Zero is correct, but what does this mean?
Terminates at U.
Yeah, how many edges are terminating at U? Do you have any edges going into U? No, so this is equal to 0. What is the degree plus of U? 1, because there is only one edge going out of U, right? Same thing. What is the degree minus of V? And what's the degree plus of V?
1, 0.
Yeah, so the degree minus means how many edges are entering into V? We have only one edge entering, right? So 1. And how many, the degree minus, how many edges are starting from V? We don't have any, so that's 0. Okay? So you got the idea what's the degree plus and degree minus? One thing I wanted to mention before going to solve this example, which is related to the undirected graph or even the directed, okay? One thing to keep in mind that graphs are, what do you call it? Let's call it without the, like the exact technical word. Graphs are not changed if you move around the vertices. Okay? The graph stays the same. If you keep the connectivity between the vertices the same, moving around the vertices doesn't matter. So for example, if you have this graph, and this is U, V, W, Z, right? This is exactly the same as this graph. Which will look like this. There's no difference. Those two graphs are exactly the same. Because you have what? U connected to W, U connected to W. U connected to Z, U connected to Z. V connected to W, V connected to W, V connected to Z, V connected to Z, right? So moving those guys around, flipping them, or doing any such games, it doesn't matter. The connectivity is the same. Those are two exactly equivalent graphs. Why does this matter? Why you have to keep this in mind? Because, for example, in a couple of slides, we will learn about something called cyclic graph. A cyclic graph is a closed loop graph where you have each node, each two pairs of nodes, right, connected in a cyclic way, such that they close a loop. And sometimes by looking at the graph only, you can figure out that this is cyclic, right? But you may look at this and you say, no, it's not cyclic, because it doesn't, it is, right? It's cyclic. So you have to inspect the actual property, not just look at how the figure looks like. The actual property says that you can start at one of them, move in any direction, you will finish again at the same. That's the actual property. It doesn't matter that it looks like a cycle when you look at it with your eye, okay? Because those two are exactly the same. Move the nodes as you like, it doesn't matter. خلاص? That's part of the trickiness of graphs. So don't rely on just the look. Yes, you can use the look if it's easy, but don't rely on it only. It might deceive you, okay? خلاص يا شباب? Okay, let's leave this and come back to the example that we have here. So we have here, again, another example, but this one is directed, and it tells you that you have vertices U, V, and W, U, V, and W, and you have directed edges between U and W, so from U to W, from V to W, and then the last one from U to V. Okay? Now, the first part says draw the graph. I already drew it by my hand, but draw it correctly in your place. And then it says, for each one of those vertices, find the in degree, so degree minus, and the out degree, degree plus. For each one, for U, for V, for W. Go ahead. يا حلو بعدين عليه خلاص رفع تقول لك عليه اكس عملتنا عنها خلاص عرفتها حد تاني جاي لك
If you have a certain amount of nodes,
question خفيف نجاوب عليه بس الحل
حد معاك؟
سوري صح بس مش هيغلط النهارده خلاص
ما تصعبش الامتحانات عشان كده
الناس كلها شاطره
على حد اكسس
حد تاني اي وان اس
يس مين دول؟ كان والله حاجه
بجد تخيل يعني كمية الميمز اللي انت شفتها
كده بعمل معاك
لا كمية الميمز اللي شفتها وقت المحاضرة وقت الامتحان
لا لا ظروف جدا
هو في
Is this for this lecture? كم واحد؟
فاكر ان انا واحد
معلش زي الفل بعيد كده بعيد شوف الثقة تحس بثقة وتواضع في نفس الوقت عارف في حاجة هنا ولا أي حاجة ولا خلاص ماشي ماينس ماشي زي الفل فصل السكة مش عايز تكتب كلمة خلاص يا شباب excellent so I think ما شاء الله this time everyone got it not almost ولا حاجة so you have this right U to W and U to V you have U to W and then you have V to W right I will ask you one question after that but so if you count for U if you count the N how many goes into how many terminated which is degree minus of U this is equal to 0 how many are going out degree plus of U is equal to 2 if you go to V degree plus of V is equal to 1 1 goes out and degree minus of V equals 1 1 goes in if you go to W degree minus of W is equal to 2 and if you do degree okay above degree plus of W this is equal to 0 تمام so you all got it a question for you يا شباب Question for you. Okay? And that's a typical question in graph. We didn't address it completely yet, but you can start looking at it right now. Okay? If I ask you a question, is U reachable from W? Can you start from W and somehow reach U?
No.
In this directed graph, you cannot, right? So the other way around. Is W reachable from U?
Yes.
In two ways, right? One way is indirect, and one way is direct. Okay? So keep in mind the question ده هنرجع له later, اللي هو reachability between two vertices. Okay? Any questions هنا? Yes.
If we have a certain amount of vertices and we know that they're all connected to each other somehow, they're all being used, the degree will always add up for in and outs for each of them, right?
That's a theory that we'll come to in a couple of slides. Okay? لا هو اللي بيتكلم عليه مش الهاند shaking. He's talking about in and out, so that's directed. Hand shaking is an undirected. So the first theorem about graph theory, very simple, very intuitive, but very important. Later on we'll see why. Okay? Say it's called the handshaking theorem, and it says that the sum of the degrees across all the vertices of an undirected graph. So this is a theorem related to undirected graph. Okay? If you go across all the vertices and you add the degrees of all of them, the total of that is equal to double the number of edges. Right? Okay. And again, intuitively, why? Because each edge will appear twice in the degrees. In one vertex as 1 degree, and it will appear also as 1 degree in another vertex. Right? So each edge, when you count the degrees of the different vertices, is going to contribute 2 times. So that's why when you add up all the degrees of all the vertices, you end up with double the number of edges. Okay? Any questions about the theorem? What does it mean?
Which degree is it?
Undirected graph. Undirected graph does not have in and out. Okay? Any other questions? Okay, that's the first theorem. Second theorem, and you can prove this theorem from the previous one, but I'm not going to ask you to prove any theorem. Sometimes I put the proof, sometimes I don't put it. It's just for, like, to amuse you. But I'm not going to ask you to prove anything. You can just intuitively think about where it comes from, but not necessarily prove the theorem. Okay? It says that if you deal, please concentrate. If you deal with an undirected graph, okay, and you go for that graph and you count the number of vertices that have odd degrees, those vertices, the number of those vertices is going to be an even number. Clear? طيب نعملها بالexample. Assume that I will just create now a random graph. I just created it now. It doesn't have to be any specific graph because the theorem is true for any graph. And let's assume that we have these connectivities. Okay. Okay? And maybe let's add this one as well. And then let's go across this graph and start looking at vertices that have odd degrees. Okay? Let's go through those vertices and see the ones that have odd degrees. Okay? So this one, it has, what's the degree of this one? 2. So that's even. So we don't care about this one. Okay? This one? 4 or 5? 5. So this is an odd degree, right? So let's mark this and keep it with us. So we care about this because it has odd degree, right? The next one, this one, 2, even. We don't care about it. This one, 3. It has an odd, so let's keep it with us because it has 3 degrees, right? The next one, don't care. The next one, don't care because this is even, this is even. Did we finish all of them or did we miss anything? No. How many we had with odd degrees? 2. You might go to another graph, you will find it's 4. You might go to some other graph, 2. Some other graph, 6. Some other graph, 8. It doesn't matter which graph. Always the count of nodes or vertices with odd degrees the count of those is going to always be an even number. You cannot have a graph, تمام, where the vertices with odd degrees will be, for example, 9 or 5 or 3 or 1. It will never happen. For undirected graph. خلاص? Clear يا شباب? Yes.
Because it usually the one link that has two odd edges or odd vertices on its terminals. And here in case both odd vertices are connected together.
لا لا مش شرط, ممكن يطلعوا مش connected خالص. كان ممكن الجراف ده يطلع كده. يعني I will show you a quick example يعني, right? Just ignore this line and let's draw this line. ده مش connected لأي واحد من التانيين. يعني مش connected لده أقصد.
But that one is also odd, has odd number.
إيه؟
But that one in the bottom it has
أما هو
it's odd also. But
ما-
we have 3 odd.
لا مش 3 ولا حاجة, ما هو ده ما بقاش odd يا زعيم. صباح الفل.
But still it's applies. I mean it's the same edge that has connecting two odd vertices. يعني صار تحت عليه صار it's odd.
يعني I don't see the reason. كان ممكن يبقى something else يعني.
No, I'm just asking is it the common thing?
اللي هو ايه الكومن ثينج؟ انا مش فاهم ايه السؤال.
Hassan, في two vertices that are odd.
that are odd, okay?
Is it always the case that they are connected together in the same network?
Not every two vertices that are odd are connected together. Not every, تمام? But is it that odd vertices they come in pairs? Yes, because they have to add up to. في فرق.
Okay, خلاص.
That not every, you can have more than one odd, but two together, two together, two together, two
Okay, this
together.
was the
وهكذا.
question.
So if that's the question, yes. If the question is every single odd is connected to every other odd, no. It's only that the odds they come in pairs. That's why they add up في الآخر to an even number. Okay? Okay. Any other questions?
Doctor, every even number vertices
Sorry?
is going to be odd.
I didn't hear the question. You have what?
Or, for example, this has 6 vertices.
Yes.
So it would have an odd number of 2 of them.
It doesn't matter. Even if it was, let's say for example, it was without this completely. So it doesn't want to erase everything. I don't know why. So let's use scratching out. So assume that this does not exist with all its links, right? So now we end up with a graph that has 1, 2, 3, 4, 5, right? And then if I have some of these with odd connectivity, like for example here, this will have odd connectivity. It's connected here, connected here, connected here, right? So that's one. What else has odd connectivity? This is even, this is even, this is even, this is even, this is odd, right? Because it has only one. Yeah. So you end up with 2, the total with odd connectivity. They will always be an even number, regardless of the number of the vertices in the graph itself. Okay?
For the first, the handshake, the example that we saw, it applies for the diet also. The number of all degrees is equal to the double of the edges.
Which degrees? Counted the degrees itself.
The in and out. Both.
So you sum the in and out
Yes.
together? Okay, that's true, because that shows in the next theorem. The next theorem is for the directed graph and it addresses what you are saying. I will show it to you. Yes?
But in this version of the example, I only see one odd.
لا, this is odd.
Yeah, and what else?
And this is odd.
What else? Oh,
Okay. لا, the theorem is true, don't worry. Okay. Okay. Next. This is theorem 3, which is the only theorem that we'll study today about directed graphs. And it says that in a directed graph, the sum of the n equals the sum of the out, the sum of the n degrees across all vertices, equals the sum of out degrees across all vertices. And those two numbers, which are equal to each other, they are equal to the total number of edges in the graph, E. تمام? If you do what you are saying, if you add this to this, you will end up with 2E. تمام? Just out of notation, so you don't get confused, this, when you have a set E, and you say the modulus of the set, this means the number of elements in the set. So this is equal to number of elements in E. But what's E? E is the set of the edges, right? So this is equal to the number of edges. Okay? So just earlier we represented this as small e كده. تمام? So just so you don't get mixed up with the notation, this is they call this the size of the set, which is equal to the number of elements in the set. خلاص؟ يا شباب؟ Only those three theorems, we are not going to apply them to something today. I didn't take a break, but معلش سامحوني. We have only a couple of special cases to look at for graphs. Okay. The first one is for simple graph. Simple graph means what?
They're all connected.
Not direct.
Undirected.
Simple graph means all the edges are undirected. تمام? So for an undirected graph or a simple graph, we call the graph complete if every two pair of edges, of vertices have an edge between them. Every two pairs have an edge between them. So for example here, طبعا هنا, this is a graph of one edge. There are no pairs, right? So it still satisfies the relation because there is zero connectivity in a graph that has zero pairs. It has only one. So one is not a pair. Okay? So there is zero pair of vertices and also zero connections. So this still the theorem applies here. Okay? But let's start with the sizable ones. So if you have two vertices, you need one link to connect both of them. And that's the only pair of points that you have. If you have three, then you have this pair, right? You have this pair, you have this pair, you have this pair. Any other distinct pairs that you can make out of three? No. For each one of those pairs, you have an edge. So that's a complete graph. Okay. Similarly, for four, okay, you have this pair, you have this pair, this pair, this pair, and you can also take this with this, and you have a connection. You can take this with this, you have a connection. Any other distinct pair that you can make? No. For all the distinct pairs of vertices, you have an edge. So this is called a complete graph. Okay? And complete graphs are given the symbol K, and then we put down there the order of the graph, which is the number of vertices. So K1 means complete of order 1, that's a complete graph with one vertex only. K2, complete graph with two vertices. K4, complete graph with four vertices. تمام؟ كده يا شباب؟ طيب, can anyone draw K5? يلا, try. لا انا عايزك ترسمها. لا انا عايزك ترسمها مش عايز طب كسل.
صفر 2
شوف الراجل عمل ايه؟ صح كده. هو ده هي دي اللي صح. هي دي. لا ده لسه حاجات كتير. عندك الكيل ده مثلا مش كل ده مثلا عندك الكيل ده مش كل الكيل. مية مية. اطلع لك نجمة خلاصية. كوريكت.
الكوليكتور سويت
15. تطنش.
لا
ايه ده ليه
مالي سويت لها شويه
بس هاي شكلها كويس جديدة جامد
طبيعي كده
ايوه
كيف فكرت بس دقيقة شوي
عشوائيا يعني انهي ناقص
لا انت هيك بدك تعمل خط عجيب
ايه
ايوه
ان شاء الله بس انا مو خلاص
قال لك صح خلاص
تخسر علي انا ولا انا وصيل انا
مرة صوت أنا معاك.
ياسين ماشي مرة كده يمشي الحال. خلاص يا شباب anyone wanted to check anything done طيب شباب just as and it was a nice idea the simplest way you can build a complete graph is to build on the previous complete so this is complete right K4 if you want to build K5 add node and connect it to everyone that's what you need the new node has to be connected to all the other ones now you have a complete K5 right that's one thing. The other nice observation is for any one of those, what's the degree of any node?
K minus 1. N minus 1.
N minus 1. So K4, each one of these will have 3 degrees of 3. K3, each one will have degree 2. K5, each one of them is going to have degree equal to 4. So for K, N, okay, the degree of any vertex, any, okay, is equal to n minus 1. تمام? Okay, we'll leave the next one to the next اللي هو الcycle. We'll leave it to the next time.